Hi everyone. In this lecture, we are going to discuss the transition state theory. So, in the last two lectures, we have discussed collision theory and the weaknesses of the collision theory as well as the probability factor. So, friends, when we consider the collision theory for the bimolecular reaction, it has certain weaknesses. So, here collision theory is unable to explain reversible and complicated reactions. Collision theory does not give any explanation for abnormally high rates. Collision theory fails to correlate the probability factor with the characteristics of reactant molecules. And lastly, the theory is well applicable to the gas phase but does not give satisfactory result for the solution. So, here these are the main weaknesses of the collision theory. To overcome the collision theory, we are going to study the transition state theory. So, let us discuss the transition state theory. So, here friends, collision theory was inadequate to explain the mechanism of the most of the reactions. Therefore, a more modern theory known as the transition state theory was given by the Eyring and Polony in 1935. This theory, transition state theory, it is also called as, or it is also known as the absolute reaction rate, or here the activated complex theory. So, here there are certain postulates for the transition state theory. So, here first of all discuss the graph of energy versus here the reaction path. So, here this is the just to understand the concept of the activated complex. So, here these are the reactant. First reactants are converted into activated complex, then the activated complex it decomposes into the product. So, here this is the E1, E1 is the energy of activation for the reactant, this is the E2, E2 is the energy of activation for the products. So, all of you know that here the reactant certain, first of all the reactants acquire the certain amount of energy, that energy is called as the activation energy, then it moves from the ground state to the excited state and there is a formation of the activated complex, and finally here the activated complex decomposes into the product. So, here this is the concept of the activated complex. So, let us consider the postulate of the transition state theory one by one. So, here as the reactant molecules approach each other, there is a continuous series of changes in bond distances. The changes are accompanied by the energy changes, number one. Number two, the reactant molecules are transformed into an energy rich intermediate called activated complex, or it is also called as the transition state. Number three, the activated complex may be formed by some loose association or bonding of reactant molecules with necessary rearrangement of valence bond and energy, or if it is a unimolecular reaction, the reactant molecules may produce the activated complex by rearrangement of atoms and redistribution of energy. Number four, the activated complex though unstable, actually it is a activated complex is unstable, it has transient existence, and here the activated complex is equilibrium with the reactant, and here the potential energy of the activated complex is maximum. So, here there is a equilibrium between the reactants and the activated complex. The activated complex finally it decomposes into the product. So, here the reactant is equilibrium with the activated complex, and activated complex finally it decomposes into the product. And here the last one is the activation energy of the reaction in the light of transition state theory is defined as additional energy which the reactant molecule must acquire to form the activated complex. So, these are the 6 postulates of the transition state theory. So, let us consider the mathematical treatment of the transition state theory. So, here for a reaction between a molecule A and a molecule B, the postulated steps can be represented by this following scheme. So, here the reactant A and B. So, first of all reactant A and B, it acquires a certain amount of energy and then it is converted into the activated complex, and finally here the activated complex it decomposes into the product. So, this is the equation number 1. So, here the activated complex is assumed to be endowed certain properties of an ordinary molecule and possess some although temporary stability. On the basis of this idea, Eyring was able to show that the rate constant K of any reaction it is given by the equation K is equal to RT divided by NH into K star. No doubt K is the rate constant, R is the gas constant, T is the temperature, n is the Avogadro number, h is the Planck constant, and here this k star, it is the equilibrium constant for the formation of activated complex from the reactant. So, here the k star, it is the equilibrium constant, and here from the thermodynamic, the equation for k star, it is given by the equation ln k star is equal to minus delta f star divided by RT. Here the delta f star, it is the free energy of the activation. So, all of you know that delta f is the free energy change, and here the free energy change, it has the equation delta f is equal to delta h minus T delta S. So, here substituting the value of here, so this equation can be written as ln k star is equal to minus in bracket delta h star minus T into delta S star bracket complete divided by RT. So, here the delta f star, delta h star as well as the delta S star are the free energy, enthalpy and entropy of the activation. So, substituting this equation 3 in the equation number 2. So, here equation 2 can be written as by rearranging. So, k is equal to RT divided by NH e raised to delta S star divided by R into e raised to minus delta S star divided by RT. So, this is equation 4a. This can be rearranged ln k is equal to ln RT divided by NH plus delta S star divided by R minus delta S star divided by R. This is the 4b. So, here this can be where K and delta S star of the reaction are known at a given temperature. Delta S star may found. Equation 4 is the fundamental relation of the transition state theory. So, here delta S star required for use of this equation is obtained from the experimentally observed activation energy E as follows. For reaction in solution or for gaseous reaction where the rate constant are expressed in pressure unit, or for first order gas reaction with K1 in concentration unit, delta S star, it is related by EA by the expression delta S star is equal to EA minus RT, equation 5 for the first order reaction. For the second order reaction, delta S star is equal to EA minus twice RT. This is the equation number 3. For the third order reaction, delta S star is equal to EA minus thrice RT. This is equation number 7. So, here for use in equation 4a or 4b, the time in the case must be expressed in terms of second. Under such condition, the delta S star obtained will be for a standard state corresponding to the concentration unit employed in expressing the K. So, here comparison of the equation 4a and the equation K is equal to P into Z e raised to minus EA by RT. So, all of you know that in this equation P is the probability factor, and here P may have values ranging from unity for the reaction obeying the collision theory to about 10 raised to minus 9. That is the value of the P, it is in between 1 and 10 raised to minus 9. It has been suggested that such a slow reaction require not only collision between the molecules which are active, but also preferred critical orientation of the reacting molecule. So, here this is the mathematical treatment for the transition state theory. Lastly, let us consider the comparison of the collision theory and the absolute reaction rate theory. So, here in the collision theory of the reaction rate, the factor A is related to the number of collisions taking place per unit volume per second. That is why it is called the frequency factor. In the transition state theory, A is connected to the entropy of activation. In reaction involving the simple molecule, that is a molecule which can be taken as a rigid sphere, the value of A is found to be the same as Z. It means that reaction involving the simple molecule, the two theories are identical. So, for the simple molecule, here the collision theory and the absolute reaction rate theory, both the theories are same or the identical. However, for the complex molecules, the collision theory fails, but transition state theory it is still useful. So, for the reaction involving the complex molecule, then the collision theory is based on the kinetic theory, while the transition state theory is based on the importance of the thermodynamic concept. This is second point. Then the collision theory gives good result for the gas phase reaction, but it is not satisfactory in the case of solutions, while the transition state theory is satisfactory for the gas as well as the solution. So, these are the some points just to compare the collision theory as well as the absolute reaction rate theory. Friends, in this lecture we have discussed the absolute reaction rate theory, then mathematical equation for this theory, and the comparison of the collision theory and the absolute reaction rate theory. Thank you.